Number one, the velocity of a moving object in a straight line is modeled by the function b of t. The position of the object when t equals 4 is 44 miles. So it's important to remember that the position function, if we were to call that p of t, if we have that position function, then the derivative of the position function is our velocity function. Velocity is the change in position over time. V of t is dp dt. So to solve this question, we want to use a linear approximation with t equals 4 to estimate the position of the object at time t equals 3.8. So whenever you see linear approximation, I want you to remember the tangent line equation. Okay, so that's going to be y sub t is equal to f prime of a x minus a plus f of a. Just to have some continuity with our function names, because we're trying to find the position, because we're trying to estimate the position, we're going to use p prime of a, which is v of a. T minus a plus p of t. Okay, so let's plug in the given values. So you need to remember that this is going to be our a value. So y sub t is equal to the velocity at 4. So we have 3 times, now the t, that's going to be this value here, because we're using the tangent line equation to find the approximation at this point. So be very careful when you plug these values in. It's going to be 3.8 minus 4 plus the position at time 4, which they told us is 44 miles. Right? So we get 3 times 3.8 minus 4 plus 44. And we can type that into our graphing calculator here. And we get 43.4. Now, they want us to use proper units because we're talking about miles. That means that our linear approximation is going to be 43.4 miles at time t equals 3.8. Okay. Number 2. Particle moves along the x-axis at time t equals greater than or equal to 0. Its position is given by this function. Determine the total distance traveled by the particle from 0 to 6. Okay, so please remember that distance traveled is going to be, if our graph looks like this, the distance traveled is going to be the sum of these distances over time. If we start here. So let's use our graphic calculator for this. This is definitely allowed. So x of t, we're just going to just write the function in terms of x so it graphs nicely. So x to the third power minus 3x squared minus 24x plus 12. And they tell us that it's only defined from 0 to 6. So I'm going to put my domain restriction 0 less than equal to x less than equal to 6. Okay, and let's see what this graph looks like. I'm going to zoom out. Find our maximum and endpoints. So we can see that the distance traveled, the first thing we need to do is find the distance from here to here. So that's going to be 12 minus negative 68. And then we're going to take the distance from negative 68 to negative 24. So that's going to be 68 minus 24, which gives us 44. And we need to add those two numbers together. So 80 plus 44, which is 140, 124. So our total distance traveled is going to be 124. It's the distances from the top to the bottom, our max to mins. So I'll write that out. We have 12 minus negative 68. That's the distance traveled downwards. And then negative 68 minus negative 24, or 68 minus 24, that's the distance traveled upwards. So we add those two together. So our total distance equals 80 plus 44, which is 124. Okay, that's question number 2. So question number 3. Particle moves along x-axis of velocity is given by v of t, whose graph is shown below. So this is our velocity function. Might pay to label that. The inflection points of the graph are marked with green circles. Find all intervals of time when the speed of the particle is increasing. Okay, so remember, speed is the absolute value of velocity. Okay, so we need to look at this graph as our velocity at time 0 is around 3.5, and then the velocity drops down to 0 and then approaches from 0, the velocity becomes negative, which essentially means from this point to this point, our particle is moving backwards. Okay, so having a negative velocity just means that it's moving backwards. Okay, so we can look, remembering that speed is the absolute value of velocity, and they're asking us the intervals of time when the speed of the particle is increasing. The speed, being the absolute value, increases up until t equals 8. Then the velocity starts to go back up towards 0. That means that it's slowing down. Okay, it's slowing down until it reaches a velocity of 0. And then from 16 to 18, the velocity is increasing again. So our intervals are going to be from 2 to 8 and 16 to 18. Okay, this might seem counterintuitive, but remember our velocity is the, sorry, remember our speed is the absolute value of velocity. So as this particle reaches at time t equals 0, this velocity is 0. So that means the speed is 0. And then all the way down here, when t equals 8, our velocity is -6. So that means that our speed is 6. okay? All these other points here are speed. It goes from 0 to 6. So that means that it's increasing. The speed is increasing. As we go from this point back to 16, our velocity is 0. That means our speed is 0. So that means our speed is going from 6 to 0. So over this interval from 8 to 16, our speed is actually decreasing from 6 back down to 0. So we don't count that. We only count this region here where our speed is increasing. Not velocity, our speed. Okay, and past here, our velocity is 0, and then from 16 to 18, the velocity approaches what looks like it's like 2.4 or something. So our velocity here is 2.4. So that means that our speed is also 2.4 at this value of t. So our speed actually increased. It went from 0 to 2.4. So we have to include this region as well. Okay, so our intervals are going to be 2 to 8 and 16 to 18. Okay, number 4. A particle moves along the x-axis so that at time t is greater than 0, its position is given by x of t equals t cubed plus 7t squared minus 49t. Determine the speed of the particle. Well, remember in the previous example, we said the speed is the absolute value of velocity, and velocity is the derivative of position. So what we need to do is take the absolute value of the derivative of the position function x of t. So let's first find the derivative and then take the absolute value at t equals 3. So we'll take the derivative, that gives us 3t squared plus 14t minus 49. So now we can plug in 3 to find our speed. Speed s of t is the absolute value of x prime of 3 of t, so we should go plug in 3. Luckily, we have our graphing calculator for this. So we can type absolute value of 3 times 3 squared plus 14 times 3 minus 49. Save ourselves some time. We get that the speed is 20. Number 5. Particle moves along the x-axis such that its velocity is given by this. Determine all intervals when the speed of the particle is increasing. So if speed is increasing, we're essentially taking the second derivative. We're taking the derivative of the speed function to determine when it is increasing. So we need to find s prime of t. So let's first, oh, they give us the velocity. Great, we don't need to use x prime of t. They give us the velocity function, v of t. So let's plug this into Desmos to get our s of x equals the absolute value of negative 8x cubed plus 24x. And we only care about when x is greater than 0. Okay, so we've just graphed our speed function as the absolute value of the velocity. So to determine all intervals when the speed is increasing, all we have to do is look at this graph, right? We can see that the speed, the line g of x is increasing. So we can say f prime of t is greater than 0 at the interval 0 to 1. And what is that, 1.732 to infinity. Just checking to see that our graph does increase forever. And yeah, that's it. 0 to 1 and 1.732 over 5 to infinity. Okay, so our answer key wants this to be in exact values. So we need to determine what 1.372 is in exact values. So because s of t is the absolute value of this function, we need to determine when does this function equal 0. So let's solve that quickly. So it means t is square root 3. Okay, so our velocity function is 0 when t is 0 and when t is square root 3. So that means that this value here is square root 3. So our answer is going to be our speed function. So I'll just confirm that. Yes. Our speed is increasing over the interval 0 to 1 and root 3 to infinity. Okay. Question number 6. The radius of a circle is decreasing at a constant rate of 6 centimeters per second. Okay, let's start off by writing dr dt equals -6. And if you want to put units, you can. 6 centimeters per second. At the instance when the radius is 5 centimeters, what is the rate of change of the area? So they want us to find dA dt. And they tell us that r equals 5. So let's remember that the area of a circle function, area equals pi r squared. So to find dA dt, we need to take the derivative of this function, the derivative of this equation, which is going to be 2 pi r dr dt. And now we can plug in our values. So dA dt must equal 2 times pi times radius 5 times dr dt, which is -6. I'm going to plug that into our calculator. 2 times pi times 5 times -6 gives us -188.496 if we round correctly. Okay. They don't ask for the units, but it might help to put the units. Because this is in centimeters per second, our area, our dA dt is going to be in square centimeters per second. Okay. On the AP exam, don't put boxes around your answers. Just write them as is. So I'm going to leave that just like that. They don't want boxes. Okay, that was question number 6. Number 7, the area of a square is decreasing at a rate of 79 square meters per second. So again, we're going to write our given information. dA dt is equal to -79 square meters per second. At the time the area of the square is 36, So its area is 36. What is the rate of change of the perimeter of the square? So we want to find dp dt. Okay, so please recall that a square has an area of the side length squared, right? And a perimeter of 4 times the side length. So if they're telling us that the area of the square is 36, that means that the side here must be 6. Okay, let's create an equation to define P as a function of side length, or let's create a function to define P as a function of area because we have dA dt. So this is the tricky part. If P equals 4s and s squared equals a, we need to solve for s first. So we get square root a equals s, and therefore P equals 4 square root a. All right, so now we have an equation for perimeter in terms of area. Now we can take the derivative of this with respect to time and get our dp dt. So to find our derivative with respect to time of this equation here, we take the derivative, square root of a, the derivative of square root a is going to be 1 over 2 root a, capital A, sorry, times dA dt. Okay, this part is a bit tricky to know how to set this up. You have to write an equation for one variable in terms of the other so that you can take the derivative of that equation with respect to time. Notice they gave us dA dt, right? So it's going to be very helpful for us to define the function p in terms of a, because when we take the derivative of that and we apply chain rule, we have to take the derivative of the inside as well. And I use the phrase chain rule kind of interchangeably with, oh, yeah, it's chain rule. We're using chain rule here. Derivative of the inside times derivative of the outside. So simplifying this, we get dp dt equals 2 over square root a times dA dt. And now we can solve for dp dt by plugging in our values. So we have 2 over the square root of 36 times negative 79. So 2 over the square root of 36 times negative 79 times negative 79 gives us negative 26.333, repeating. So that's our answer. Oh, and if we use our units, this is going to be meters per second, because perimeter is one dimensional, right? Perimeter is the distance around, it's these linear portions around the square, and those are measured in meters, not square meters. All right, question number 8. This is fun. The length of a rectangle is growing by 2 inches per second, and its width is growing by 3 inches per second. Okay, so let's write these down. dl dt, it's growing by 2 inches, so it's going to be 2 inches per second. And dw dt, the width is growing by 3 inches per second. Find the rate at which the area is changing when the length measures 7 inches and the width measures 3 inches. So we need to recall that the area of a rectangle is length times width. And they want us to find the rate at which A is changing. So they want us to find dA dt. So this we're going to apply product rule. So we have U prime. So let's label this U and V. U prime V. So it's going to be dL dt times W plus V prime U dW dt times L. And we just plug in our values. So they told us that's 2 when the width is 3 plus dW dt, which is 3 when the length is 7. Right. It is past midnight here, so I'm not doing this in my head, even though I'm pretty sure we all can. So we get our answer is 27, and the units are inches squared per second, because area is in square inches. Okay, number 9. The short leg of a right triangle is shrinking by 2 inches per second. So I'm going to draw this out for you guys. So the short leg is shrinking. So let's call this x, let's call this y. You can say dx dt, the distance from the origin out to this point here on the x direction is -2, because I say it's shrinking inches per second. And the long leg is shrinking, so we can say dy dt is -5 inches per second. Find the rate of change in the area is changing when the short leg measures 21 and the long leg measures 28. Okay, so we need the formula, or sorry, we need the equation for the area of a triangle, which is 1/2 base times height. Here I've labeled base x and height y. So we need to find dA dt. Again, this is product rule. We have a 1/2 in front, so I'm going to put 1/2 in front. And let's just use product rule U prime V. So that's going to be dx dt, or x dot, I use dx dt, times y plus dy dt times x. And yeah, go ahead. Again, just like the previous one, you can plug in our values. So you get 1/2 dy dt was -2 when y, the long leg, is 28, plus -5 times x, the short leg, which is 21. Okay, to our calculator we go. 1/2 -2 times 28 plus -5 times 21. We get -80.5. This is going to be square inches per second. Okay. Number 10. The f be a differentiable function such that f of -1 equals -7 and f prime of x equals -3x plus 3. What is the approximation for -0.95 found by using the line tangent to the graph of f at x equals -1? Okay, so another tangent line approximation question. So let's remind ourselves, this is going to be f prime of a times x minus a plus f of a. Okay, remember a is not the value that we're approximating, it's the value that we're given to approximate with, right? So that means that this is a, and this we're plugging in for x. Okay, so we want to find f prime of a, we want to find f prime of -1 times -0.95 minus -1 plus f of -1. Okay, so they give us f of -1. This is -7. So let's put that there. I'm going to use my calculator to add -0.95 plus 1. So that's going to give us 0.05. And we need to find f prime of -1. So we need to plug -1 into this equation for f prime of x. Okay, -3 times 3, -1 is 3, equals 3 is 6. So we have 6 times 0.05 minus 7. We get -6.7. All right. Number 11. This one's a little bit tougher. The f of x be the function f of x equals -3x to 2/3. What's the linear approximation for 8.1 found using the line tangent to graph at x equals 8? Okay, so again, we need to use the tangent line approximation function equation, and we need to determine what f prime of x is to get our slopes. Let's do that first. Let's find f prime of x is going to be -3 times 2/3 x to the -1/3. Okay. We know we're going to need to plug in x equals 8 into our tangent line equation, so we might as well just do that now. We need to find f prime of 8 as well as f of 8. So let's cancel this out. This 3 and this 3 cancel out, so we're left with -2x to the -1/3. -2 times 8 to the -1/3, which is really -2 over 8 to the 1/3. Who's texting me? Okay. And 8 to the 1/3 is just 2, so this is going to be -1. -2 over 2, which is -1. Okay, so we found f prime of 8. We also need to find f of 8. So we're just going to plug that directly into here, which is -3 times 8 to the 2/3 power, which is -3. Well, 8 to the 2/3 power is 4. You should know that from algebra 2. So that's going to give us -12. Okay, we have everything we need. I'm going to switch colors so that we can solve this. The tangent line equation, it's going to be -1 x minus 8 minus 12. And we can use our graphic calculator to check this. So let's type in f of x equals -3 x to the 2/3. And when x equals 8, we want our tangent line equation to be y equals -1 x minus 8 minus 12. Okay, and we can see that that line is tangent to the curve at x equals 12. Sorry, x equals 8. Okay, so now we can use this function to find our approximation. So we're going to replace x with 8.1, and it's going to give us a value of -12.1. Okay, when blank, the second derivative blank, not sure what they're asking us to fill in here. When x is greater than 0, the second derivative is, okay, yeah, because x equals 8, we're going to use x is greater than 0. The second derivative is also greater than 0. And we can tell that because it's concave up. If you wanted to take the second derivative and then plug in 8, you would see that it is positive. And Desmos can do that for us very nicely. So I'm going to take the second derivative of 8, and it gives us a positive number. So the second derivative f of x is f double prime of x is greater than 0, meaning that f is concave up. Near the point of tangency, making the value of my approximation an underestimate. Okay, so if we draw our tangent line, again, let's put that back. We can see that the tangent line is under the actual curve. It's below the actual curve. So that means that the tangent line, any values that we get from our tangent line are going to be under approximations. Okay, and you can see that if we plug in 8.1 here, we get negative 12.1. But if we plug this value directly into the function itself, we get negative 12.09, which is slightly higher than negative 12.1. So this is an under approximation, or linear. Okay. Oh, last but not least, I think this is the last question. Yeah, number 12. Given the selected values of function f as derivative below, determine the value of the limit as x approaches 1 of that thing in its simplest form. If the limit does not exist, write dne. Okay, so I think this is an application of L'Hopital's rule, right? Let's check. All right, first, let's do direct substitution. That means we're going to plug in 1 into this equation and see where our limit is. So we get 2 times f of 3 times 1. So we're plugging in 1, plugging in 1. That's a 3 times 1, not 3.1. 3 times 1. So f of 3.1, f of 3 is 10. So we have 2 times 10, which is 22 over 0. Okay. You might be tempted to slap L'Hopital's rule onto this, but remember, L'Hopital's rule can only be used when you have 0 over 0 or infinity over infinity. Okay, so because we have t equals, because we have our limit as x approaches 1 is 22 over 0, this is our limit has to be either infinity, negative infinity, or does not exist. Okay, so to determine which one it's going to be, we're going to look at the derivatives of the neighboring values for when x equals 1.